In this highlight video, we will talk about the halogenation of the alpha position. After you watch this video, you should be able to predict products and write the mechanisms for the halogenation of carbonyl compounds under both acidic and basic conditions. Under acidic conditions, a proton at the alpha position can be replaced or substituted for a bromine or another halogen. Like we might expect, the first step of this mechanism under acidic conditions is protonation of the carbonyl oxygen. In this example, we're using, this is HOAC, and this is just a shorthand for acetic acid. Remember, acetic acid is the component in vinegar. Protonation gives us this intermediate here, which, remember, increases the acidity of the protons at the alpha position. So we can take the conjugate base of acetic acid that deprotonates this alpha position. Form the enol. So the enol under these acidic conditions is going to be the nucleophile. It can then react with bromine like this to form brominated species that has the carbonyl protonated again. Like this. And finally, deprotonation with, we can just say use bromide here to balance our equation, gives us our product. You might have the question whether this bromoketone here would actually react one more time to form a dibromo species. The answer is that under acidic conditions, this reaction will take place only one time to add one bromine. Only one time. The reason is that once we've added a bromine, we can show this in two different places. The bromine, being more electronegative, pulls electron density eventually away from the carbonyl, making this oxygen less basic. And therefore less likely to protonate to complete the mechanism again. We can also show this at the intermediate just before the product. This bromine pulls electron density away. It actually destabilizes that cation. So for both of these reasons, the acid-catalyzed halogenation only takes place once. We have another example at the bottom, and this is for an iodination. We're using I2, also in acetic acid. This reaction would, like we said, would add one iodine to the alpha position to give this product. Under basic conditions, the alpha position gets chlorinated in this case, but that species can in fact react again with more chlorine and hydroxide to substitute all alpha hydrogens with chlorine. Notice in these examples I've put methyl groups on this side, so that alpha position does not have a proton that can be substituted for. So let's look at the mechanism of the basic halogenation, and we'll try to understand why this reaction proceeds to complete substitution of all of those alpha positions. So, under basic conditions, of course, we're going to go through an enolate anion as the intermediate. So hydroxide can remove an alpha proton, just push the electrons to that alpha carbon. And that enolate that's been formed can react with chlorine to give us our monochloro product. Under acidic conditions, the halogen reduced the reactivity of the ketone, so it did not react further. Under basic conditions, we have just the opposite situation. Removal of the proton at the alpha position forms another enolate. But in this case, the chlorine pulls electron density away from the anion, stabilizing this anion. Therefore, the reaction wants to react another time. Chlorine can then react with this new enolate to form a dichloro product. So, under basic conditions, the reaction proceeds to substitute all alpha hydrogens for chlorine in this case. An example of this reaction that has been used in the past as a qualitative test for the presence of methyl ketones is called the iodoform reaction, or in a more generic sense, the haloform reaction. So this reaction, like the name suggests, ends up generating this molecule here that is called iodoform. Maybe you've heard before, a more common version of this is HCCl3. This one is chloroform. So the other product ends up being the carboxylate anion. Now, this was used as a qualitative test because iodoform is kind of a yellowish or orange color. And so carrying out this reaction on some unknown material and getting a yellow product indicated the presence of the methyl ketone. All right, so let's look at how this reaction takes place. So the first part of this reaction just involves the basic halogenation reaction. So we have this methyl group. I'm not going to show all the steps here. We said under basic conditions, this reaction can proceed to replace all of the alpha protons. We're going to focus just on the right side of this, though. So this replaces all three of those hydrogens and generates this Ci3 group. Because this group is electron withdrawing, that activates the carbonyl carbon. And so in the next step, the hydroxide, because it doesn't have a proton there to remove, acts as a nucleophile and attacks the carbonyl carbon. This leads to the formation of a tetrahedral intermediate. and the CI3 group becomes a leaving group. Now, this is not a great leaving group, but it does lead to the formation of some of the carboxylic acid and this CI3 minus species. All right, so this is our leaving group. Remember, we can evaluate the leaving group ability by looking at the basicity of that species, or alternatively, looking at the acidity of its conjugate acid. The pKa of iodoform is about 25. So this is a weak acid, which means that this is kind of a moderately strong base, but it's good enough here to leave because what happens next helps the reaction from going backwards. This is a strong enough base that it now removes the proton on the carboxylic acid. This generates the carboxylate anion and the iodoform. So any amount of the triiodocarbanion that's formed deprotonates the carboxylic acid. This siphons the reaction all the way towards the product. Let's think about how this halogenation reaction might be useful for synthesis. So let's start down here. So the problem here that we're looking at is to start with cyclohexanone, and we want to end up with two different products, or be able to synthesize two different products. One with the cyano group at this alpha position, and one at the beta position. So how can we make those two products? Well, the one reaction that we really have right now is the halogenation reaction. Now, to be synthetically useful, what we really want to do is just add one halogen and not halogenate all of the alpha position. So what do we use, acidic or basic conditions? All right, so we're going to want to use acidic conditions. So we'll use acetic acid and bromine. Remember that this just adds one bromine at an alpha position. Now, we can go there directly to this alpha cyano compound just by doing an SN2 substitution. So this can come down here, displace the bromide, and we go directly to that product. So that one is reasonably straightforward. But how do we get from the bromo ketone to the compound with the cyano group at the beta position? The way that we can accomplish that is by doing an elimination reaction to the alpha beta unsaturated ketone. And then if we add cyanide, remember, because cyanide is a weaker base, it does a 1,4 addition. Okay, and it puts that cyanide at the beta position. So this step here is just probably an E2 elimination. I think there's a variety of bases that you could use. I've seen pyridine used. And our book likes to use a combination of lithium carbonate, lithium bromide, all in dimethylformamide. All right, so this is a way that we can bridge the reactivity at the alpha position with the reactivity at the beta position. Then the 1,4 addition gives us this beta cyano